Hello. Um, Today I will be talking about a new topic, which is solar photovoltaic and wind energy conversion system. So uh, this is a pretty straightforward example that we're gonna do. I have actually uploaded a couple of videos regarding this. So, for instance, renewable energy 101, solar energy on 101, how solar PV power plant works, then wind energy and how do wind turbines work. So these are very common, very basic videos. I think it'll really help you guys. So now let's go to so you'll find a simulating file over here. So all you have to do is download it, and let me open the file. So this is the file. So all you have to do is download it, but download and run it. But before doing anything, I'd like you to actually go through all of them. And so this is PV farm, which is 8 megawatt. So if I double click on this PV farm, you'll see that the efficiency is only 10%. So you can definitely change the efficiency, but I would not recommend you to actually use which is below, like not above like 18%. Then this is the area of the PV plant. Now if I click on the below arrow, this arrow, then you will see the system. So this is the solar converters equivalent circuit, and these are the different equations that you need to actually do to represent a PV farm. So you can use these blocks to actually calculate the measurements, like power measurement, voltage and current measurements. So from here you can, if you double click it, you will see the measurements. So these are the description of this block parameters you can see here. And if I double click it, I will see some graphs regarding PV. So what are the outputs of PV? So we can get it from this oscilloscope. So I have already, I guess I have, I'm not sure whether I ran it or not. Okay, so I ran it. So this is the power I'm generating from the PV. It comes from certain input. So if I click here, it's the irradiation profile. So if I double click here, you will see the irradiation profile is given here. So I can actually change it, like the solar irradiation actually changes depending on the time of the day. So sometimes it's very low, sometimes at noon time, especially when the sun is like above our head. At that time, the irradiation is at its peak. So we can actually change the irradiation depending on the profile. I will try to actually provide another uh, solar thing, so where you can actually change it. Anyway, for this experiment, I'm not gonna suggest you to change anything here. So this is the solar PV farm. So if you double click or go to this block, then you can see the equivalent circuit. So same goes for wind farm. We have a wind farm system here. If I double click it, so I will see nominal voltage. You can change the voltage, but you need to actually change some of the key parameters on the wind profile. Um, Not in wind profile, like because of this wind profile, we have chosen the system to be this much, right? So it has some sort of relation, because we actually, when we design a wind farm, first we design the wind profile of that area. If the wind profile is good for the wind farm to be designed, then only we go for the design. Otherwise we don't go even. And Depending on the wind profile, we say this wind farm will be this big. Anyway, I'll try to show another example here. Let's see. So why I chose this one, because it's combined with like PV, wind, and conventional power system. So that's why I chose this one. Anyway, I'll show you another one. So yeah, if you want to change it, the nominal power, nominal wind speed, and maximum wind speed, we can change it definitely. By before doing that, we need to change the wind profile. If I double click the wind profile, you'll see similar type of arrangement where you can actually change this wind profile. So we can definitely change it, but there is another easy way. I'll show you that later. So this PV farm actually is producing three-phase. Although we know normally PV they produce DC, but since we have a PV farm system here, so that means it includes an inverter circuit. So although it is getting DC, but with the help of an inverter, it's actually producing AC power to the grid. Then the final one, which is the diesel generator here. If I double click it, this is the generating section. So this is a synchronous machine, synchronous generator, typical synchronous generator from, and this is the transformer, and these are the outputs of this unit. So these are excitation system. If you are familiar with the synchronous generator, so you can actually learn a thing or two about this synchronous generator setup. So we know that a synchronous generator requires excitation to the rotor. So this is the block where the excitation, the field excitation is feeding to this generating station. Generator. And we have governor control, which controls the speed at which the turbine is rotating. Like the turbine, I mean like synchronous generators rotor is rotating, so it is that. So it controls the flow flow of like piston, since it is a diesel generator, so that means the piston are like changing its position, and by which the rotor is rotating. So it controls the flow of that piston, and we can actually see the diesel generators power output. So this is P and Q, and these are the three-phase output that we are getting from this. Then this is the grid. So this is it's not a grid, you can say, but it's a miniature version of a grid. So this is the transmission line, you can say, and we have a transformer. After the grid, we are actually, let me see, so this is Y connected, Y, and if we look at the parameters, so nominal winding 1 is this, winding 2 is this. So that means if I look at this one, winding 1, that means the left hand side, which is 25 kilovolts. So this is the grid side we're talking about, and winding 2 is 600 volts. That means this is the distributed section. So at this area, we have residential load and industrial load. These are the values. So residential load is 10 megawatt, industrial load is 0.16 megavolt ampere, and the power factor of residential load is 0.15. And we have a vehicle to grid system. So this is 4 megawatt. So this is representing various aspects. So rated power is 40 kilowatt. So 4 megawatt. Okay. so sorry, 40 kilowatt into there are hundreds of them, so that means 4 megawatt. So system's efficiency is 90. Vehicle to grid, so from vehicle we're supplying to the grid, and in some cases we also, when the electricity is needed for this EV system to be charged, we actually get electricity from the grid as well. So number of cars, there are 35 in profile 1, in profile 2, 25, in profile 3 it is 10, profile 4, 20. So there are a number of cars actually. So you can say it is a charging station where, or you can say in a residential area, in this block there are 35 number of cars actually um, pushing its power to the grid. So so the arrangement could be in various ways. It could be in a block, sorry, in a parking station or charging station or in a shopping mall or anywhere. Like in residential areas, there are like 5 blocks. These are the 5 blocks profile that we are seeing right now. So if I run it, uh, I already ran it, but I totally forgot. Let me see. So it will show you 1 day span, like that means 24 hours simulation of PV, wind, and microgrid system. So this is kind of a microgrid, you can say. So it's actually not connected to outside world, outside other places. So it's self-sufficient. So this microgrid is self-sufficient to provide its power to its residential loads, industrial loads, EVs, etc., etc. Oh, I forgot to actually mention about this residential load. Let's look into it. So this part, if I like, I have actually double clicked it. So the top section is the industrial load where different types of representation of induction machine is given. So this is asynchronous machine. So it's you can say an industry having this load. So if motor normally is turned on at 3 a.m. So it's programmed to be like this. So at 3 a.m. it will turn on and it will work. After that, it will stop at 12 a.m. And we have residential load. If I double click it, so what is an asynchronous machine? Machine is nothing but an induction machine, which is scroll case type, just like the machine we saw last class. So you can go through different parameters of it. So what's the nominal power? It is this much, 1.5 to the power 5. That means um, 0.15 megawatt, yes. Then the voltage is line to line voltage. It requires 600 volt, and this is the frequency, which is 60 watt, 60 hertz. Okay. So if you want, you can change the parameters, since these parameters, not the voltage, I would say you can change the parameters of other aspects like power and all, just to see the changes. I know um, it, it's not too complicated actually. So we can change the parameters of different parameters. Say for example, PV, we can change the parameters of wind, we can change the parameters of this diesel generator. So now let's talk about the residential load. We have residential load. These are the nominal power is this much, power factor is 0.95. Now that's why I was a little bit confused. So it is not 1.5, it is 9.5, it should be. And this is also, if I look at it, the power factor is 0.95, not 0.15. 0.15 is too low. Okay, so these are the two values. If I want to see inside, so I will see these are the loads, and these are the control parameters and how it works. So these are two loads representing this residential load, and you will see the load profile here. Okay, now let's see different outputs. So time, so 24 hours. Now let's see. Okay, so it's a little bit difficult to actually understand what this is in first go, but if I put it side by side, then you will understand. The first one is load, which is yellow. Yellow is the load. This one is the load section. So different changes in load in with respect to the time. So first hour the load was like this, second hour is this, third hour, fourth hour. As the time is going on, the load is also changing. The second one is total power, which is blue. Okay, then we have diesel contribution, which is red. This is the diesel's contribution. So this is blue, and this is what is it called, load. So load and the total power, they are actually following each other because of the load. Total power is actually extracted from different sources. Now if I now the last three will be shown here, sorry, last three, which is red, then solar, which is this one, green, and this is magenta. So they are actually sharing the power between the loads. So say for example here solar's contribution is 0, but at this hour solar is starting to actually kick in, and if you look closely, then at this point this what is it called, diesel, we are not actually requiring that much of diesel. That's why the diesel's part went down. And the wind, in case of wind, if I can show you the pattern, the wind's pattern is just like this, and solar's pattern is just like this. What does it mean? It follows the profile of wind and solar. So no matter how powerful your wind farm is there, if there is no wind, then we won't be able to get any power from the wind. So it follows the pattern, and if these solar and wind, they are not sufficient, then at that time this diesel kicks in at this moment. If you look at it, the wind is not enough, solar is completely zero, but the rest of the power is actually served from this diesel generators generating station. Okay, so I want you to actually play with it so that you can understand how it works. So I'm gonna give you another one. Let me just give me some second. So this is another solar example. So this is 100 kilowatt grid connected PV array. It's a detailed model. So in here you will see more details here. So we have the utility grid, which is connected to this PV system. So if I go from the left, you can see the PV array here, which is actually getting its input from this irradiation index. So if I double click it here, you will see that in different time of hour, like for instance, the span is 3 hours, say for example. So although it's says that it is seconds, say for example this is 3 hours. So first 0.75 hour, it gives you 1000 what is the watt per meter square. So this is 1000, and after that it declined and it reached around 250. Then again it went back to 1000, then it came back to 250 again, and so this is the pattern. Say for example, so we will get the power according to this profile. You can change the profile. Say for example, if I want to change it, I can change it like that, or I can change the value, like say, like I can change the value just like typing here. Anyway, so this is the irradiance profile. With respect to this profile, the PV will actually generate its power. So this is a more detailed design, so you can choose your module type here, and how many number of modules will there be, and how many number of parallel strings. I guess during the class, like power system class, you will uh, learn something about this. So I'm not sure whether the teacher covered it or not, but definitely it will be in the, like, what is it called, syllabus. Anyway, so the thing is, there are number of series connected module per string. So number is 5 and number of parallel string is 66. What does it mean is, like, series connected. Say for example, let me give you an example. So if this is one module, so there are cells. So if you in a module, when we buy solar panels from a vendor, they give us a module. So if those modules are either 12 volts, 64 volts, 24 volts, depending on, like, so the voltage may be different. But depending on our requirement, we actually connect them in either series or parallel connection. Okay, let me give you an example. Solar PV array. Okay. So say for example, this is one module and this is another and this is another. They are connected in series. So with series connection, and this is a parallel connection. So in series connection, we are increasing the number of voltage from this point and this point. It will be 3 times the voltage of individual module. And in case of a parallel connection, the voltage will be the same, but the amount of current we are going to get is larger. So with our requirement, design requirement, the solar modules could be in series connected or in parallel connected. So this is one array, you can say. Um, so this is connected, series connected modules per string and number of parallel strings. So if we have 5 series connected, then those series connectors will be connected in parallel so that we can get a huge number of current, because although the voltage is very high, the current might be very low. So but we want a balance, so that's why we need to increase the amount of voltage by connecting series connected modules. And also after those connections, these identical 5 um, 5 series connected modules, we have 66 number of these series connected modules in parallel. So the total number of module will be 66 times 5. By this way, we can achieve our desired ampere or and like voltage in the PV array system. So you can choose any of the companies, but their profile is totally different. According to this, you need to change the value. Anyway, so like the output of a PV array is normally DC voltage. So their voltage level might be different. Like for instance, the voltage is output voltage is, say for example, in this case, let me run it. I totally forgot what the voltage level is here. So the array voltage level will be something, but we need to actually boost the voltage. That means step up the voltage. So DC, we don't have DC. So yeah, we can see that the array's voltage is 249, in some cases 256, 274. So it is keep on changing, but we need to have a boost circuit, which actually is a step up transformer type of thing, but for DC systems. See, the irradiance are changing, and with regard to this one, the voltage is also changing, but we cannot have fluctuating voltage in our system, right? So we need that's why we need a boost circuit. So this is the boost circuit, and after that this boost circuit will give you 500 volts fixed voltage. In some cases it might be fluctuating, but that's why we have these two diode connected here, so that the voltage key, like voltage inverter is seeing from this point, is always fixed. So these booster circuit boost converter is 5 kilohertz, 50 volts, sorry, 500 volts boost converter, which boosts the voltage which is getting from this PV array. And after that, this 500 volt DC is feeding through this diode clamp, diode DC link capacitors. These are capacitors, not diodes. I apologize. So these DC link capacitors are connected with this 3-level voltage source converter or inverter, where the input is DC and the output is AC. So this is a 33 times 60 hertz, um, 500 volt 3-level voltage source inverter. So we are gonna get approximately 500 uh, 500 volt on the DC side. We'll get somewhere around like 250 to 60 voltage on the AC side, since it is getting 500 volt, because there are some losses. And also this 500 volts is splitted into two to make an AC, so it will be approximately two, not two exactly. So uh, so it will become AC, and it will reduce the amount of voltage. However, these, so although we are telling that this is AC, but in reality it is actually not AC. It is um, it is AC, but with some noises. Like there will be some noises, so not perfectly sinusoidal. So that's why we need to use RL filter here, RL filter. So this filter will give you AC output. You will see, let me see whether I can show you that one or not. No, this is not the one. Yeah, here you go. So this is the output of this inverter before using the filter. But if I look at here, now you'll see after the filter, the waveform looks more like a sinusoidal. So you can say that these filter circuits are essential. Then we have a step-up transformer, which is an AC transformer, and it is connected to the grid. So what are these? These are actually controlling this inverter, and this is controlling this boost converter. You don't need to actually know much about it right now, because you're going to do some courses related to this one, like power electronics. You will learn the control circuit and like their control mechanism, like current regulator, voltage regulator, PLL, you will, and PWM generator. So you will learn those over there. So yeah, so I want you to run this and see different sorts of like outputs. So like say for example, this is the irradiance profile, this one, the last one. And according to this area irradiance, the power of the photovoltaic cell is this much. So, and this is the voltage, and these are the duty cycle. What does duty cycle mean? At we at It is a rate at which these switches, like this IGBT1 and there are 6 IGBTs here, so how they actually are turned on and turned off. Okay, so I want you to actually run this and make a short um, report on this one as well as the other one. So I have another example, which is a wind farm. So if I double click here, you will see wind farms example. So don't take these 3 examples to like if you don't understand many of the things, it's okay, but I want you to have a basic idea what wind farms like look like and what are the different elements to it and how do we actually connect this wind farm to the normal grid. So this is the grid. There are some bus bars here. So this is one of the bus bars. This is another bus bar. This is another bus bar. So the power is coming from this. This is a plant, you can say, or this is utility, you can say. This is 20 kilometers of transmission line. This is 10 kilometers of um, transmission line, you can say, or distribution line. So wind is actually supplying power from right to left, and this grid is supplying power from left to right. So if I double click it, you will see some parameters here. This is the amplitude, the voltage, phase to phase RMS voltage, and this is phase degree. So is there any phase like shift are there or not? And this is the frequency, load flow. It is a swing type of generation. So whatever the power is required from this section, it will actually supply this much. So then we have a transformer here. It is uplifting the voltage from, sorry, not uplifting, sorry, stepping down the voltage from 120 kilovolt to 25 kilovolt. So then we have 20 kilometers of distribution line. Then again 10 kilometers of distribution line. We have a load here. If I double click it, it's a industrial load. So we have a, what is it called? Power plant, which not power plant, any type of mill, you can say MILL mill. So where asynchronous machines are there. So this is an induction machine. This plant is 2 megavolt ampere. And we have another load, which is a resistive load, 500 kilowatt. So now the power is coming from this side and this side. Let's talk about the wind farm. So if I double click here, you will see there are 6 number of units. Each wind turbine is 1.5 megawatt. So that means 6 times 1.5 megawatt is the total wind turbine plant's power. And there are other parameters, line to line voltage, frequency. These are given here. Stator's values are given here. Now that's the generator part. If I click on the turbine, it will show you this much value, which is similar. Now there are values of different aspects of wind turbines. Say for example, maximum pitch angle. You don't need to touch any of them. This is the converter, so the values will be 6 times of anything. So if you change the value, for instance, 6 from 6 to 12, then you need to change it from 6 to 12. And you don't need to take any you don't need to change any of other parts. Control, I'd not recommend you to touch any of this. So it is this wind turbine requires wind. So where does it come from? Let's see. So this is one wind profile for a whole day. So this second represents 1 second represents 1 hour here. So at this time, which is at midnight, it was like 10 is the value. That means 10 meter per second. And this is 11 meter per second. Sorry, 10.2 meter per second. No, 10.4. And this is 9.6. So this is actually a wind profile I collected from it's I guess it's from San Francisco or some other cities. I don't know. I can't remember, but it is an actual wind profile. So if I run it, then I will see that. By the way, there are trip mechanism for wind turbine protection and plant protection. Okay, so if there is any sorts of what is it called, malfunction in the system, then we'll see that it will trip. The wind turbine will trip for it to actually save the plant, and also um, this industry also has its trip mechanism. So now let's bring the results. I guess you can see them here. Okay, on the left hand side, we have the wind turbines results. You can say this is the positive sequence voltage. This is the positive sequence of B575. That means which is coming from the grid. Let's see which one is what. So yeah, B75, sorry, 575. That means it is this one. So the power of this bus bar. So this is this one, sorry, voltage of this bus bar. So the current of this bus bar is this. Generated power of this bus bar, that bus bar, which is closer to the wind turbine system, and generated Q. This is VDC. This is the speed of the turbine, and this is the wind speed. You will see the speed is different than this one, because when it starts to rotating, after when even if it is going down, it still has some inertia. That's why it is not losing its power. Sorry, it's not losing its speed. So it has some inertia, so even if it is the wind speed is not there, in some cases it will still run. And we have on the grid side, we have voltage VABC on bus bar 120 and VABC for bus bar 25, and this is VABC for bus bar 575. This is the power. So initially the power is coming from the wind turbine, but since the wind is very low here, so the power is going down. So at this point, the grid is giving the power. See, here the wind turbine's power is going down, but here at this point, all the powers are coming from the grid side. So I want you to actually run the system, run these three files and give me what you think. I'm not gonna give any instruction on this. I'd like you to actually run them, and whatever you've understood, whatever you feel that okay, this is important, whatever you feel okay, um um let's talk about let me change some of the stuff and change it and see whether it if has any effect on it or not. So it's an open book type of thing. So you change the parameters and see what happens, because I want you to actually dig deep and try to understand what's going on. So anyway, so I'll give you these 3 files, and the report doesn't need to be very big. It can be 2 or 3 pages long. It's okay. Um, you don't need to write too many stuff. All you need to do is run the simulation and give me the results. That's it. So I'm gonna give you these 3 files. So if you have any question, you can definitely reach out to me. You can email me. So that's all for today. Thank you so much.